presentation is from an Italian top scientist on operational model analysis and health monitoring of bridges. Is Professor Carmelo Gentile from Politecnico di Milano. And the title of his presentation is Non-Destructive Testing and Monitoring of Masonry Arch Bridges. Carmelo, you can start.
Okay, this one work. Okay, thank you, Professor Carmelo, for the kind introduction. But before to begin, I would like to thank our colleagues Carlo Pellegrino and Paolo Zampieri for the invitation and for giving me the possibility of sharing some recent experience carried out by my research group on 3 different masonry bridges. Here we can see 3 pictures of the bridge I will present to you. For the first 2, on your right-hand side, we have performed the operational model analysis, testing and analysis. And the results I will show include the anomaly detection and the evaluation of strengthening effects for the first bridge. For the second one, operational model analysis was a key step in the validation of a numerical model for the structural assessment of this second bridge. Both these bridges are in the province of Cuneo. And the third investigation was carried out on a third bridge near Pavia, in Lombardy. And this project was part of a larger project promoted by the Lombardia region in order to evaluate if by using tilt meter, so a low-cost sensor, it is possible to understand something about the score effect. And the score effect is also the topic of some of the next presentation. Let's move to the first bridge. It's a bridge crossing the Gesso River in Cuneo. The bridge was erected between 1853 and 1856. You can see the bridge is a length of more than 100 meters with 3 arches of 24 meters. And you can see some damage. This picture are taken in 2019. The bridge afterwards was retrofitted, and you can see, for example, some elements of the retrofitting, some steel barrels in the intrados of the arch that were post-tensioned, and afterwards this part of the structure was injected, and there are some other limited intervention. For this bridge, 2 series of ambient vibration tests were performed before and after strengthening in October 2019 and March 2024, more or less in the same temperature condition, more or less 18-20 degrees centigrade, which is an ideal temperature for ambient vibration testing. As you can see, both transverse and vertical dynamic characteristics were in investigation, and the same sensor layout was adopted in the 2 tests. Let's come to the result of the first test related to the transverse behavior. Here we can see the first singular value line with 3 quite well-defined peaks that are corresponding to well-defined alignments of stable poles in another system identification technique. But what it is very interesting is that from these first 2 modes, first 2 lateral modes, it is possible to see very clear local anomalies in the first arch, the one that is very close to Cuneo, on the Cuneo side. And in addition, we have 2 closely spaced modes with similar mode shapes, and especially in the field of laboratory testing, this kind of behavior is often called in the literature as frequency splitting, and again, it is something that is related to damage status, damaged condition of the structure. Here we can see the overall identified mode in the first identification tests, with the first 2 I was addressing before. The first vertical mode is at a frequency of about 7 Hz. after strengthening the more or less the same mode shapes were identified, and you can clearly understand that the effect of strengthening is very highly felt, especially for the lower three modes, whose increase is in the range of 10%. Here we can see again the new mode shapes in the retrofitted condition of the bridge, and we can observe that the previous anomalies in the first two mode shapes now disappeared, and also there is only one third lateral mode. Coming to the second bridge, most of the results obtained on this bridge have been already published in 2023. The bridge is again in the province of Cuneo. The bridge, as you can see, is about 117 meter long and consists of 5 masonry arches. It is placed in the national road SS21, connecting Piedmont with the French border and crossing the Stura de Monte Valley. Basically, for some of you that possibly know this region, it is to say that there is a very well-known brand of Italian mineral water that is placed in the close neighborhood of the bridge, so their products are coming to the world, to Italy, basically crossing this bridge. At the beginning of our investigation, no documents were available on this bridge, and so the typical research that we performed involved historic and documentary research, geometric survey and visual inspection, of course ambient vibration model testing and analysis, some few coring tests, and afterward all this information were collected in two numerical model, one simplified one and a refined other, and the model-based safety assessment was performed after the calibration of the model. Starting from the historic and documentary research, we haven't found in the architect any drawing of the bridge, but we understood that the erection of the bridge was completed in 1887. Starting from 1912, a steam tramway route was installed on the bridge, and very important is the aspect concerning the central span that was destroyed, that was heavily damaged but practically destroyed during the Second World War, and was rebuilt in 1948. Now the bridge is used as a roadway bridge, and one of the other aspects that we tried to collect in the beginning was trying to understand the internal morphology of the bridge. And luckily, there are a lot of documents related to similar bridges that are dating back to the same region and to the same years of construction of this bridge, in order to possibly understand the internal morphology of the bridge. Another interesting information that was useful in our modeling was related to some pictures dating back to the damage. And for example, we can observe here a picture of the bridge before and after the complete detachment of the collapsed arch. And we can see, for example, that here the fill consists of a very good material, a material that is really compact, and in fact it stands after the detachment of the arch. Of course, with the present technology, it was possible to make a very refined survey of the actual geometry by using laser scanner and also using other combined technique. Here you can see typical point cloud of the bridge and some other local picture. And all these information were synthesized, of course, as usual, in elevation and plan of the bridge. Here you can see a complete elevation, a complete view of the elevation of the bridge, and also on visual inspection, and that were also carried out with the help of some drones. And here you can see some details about the damage that was detected on site. As I anticipated, ambient vibration tests were carried out on this bridge with one lane opened to traffic, and both the horizontal and the vertical behavior were investigated with the sampling frequency of 200 Hz, and several data sets of 2,400 seconds were collected. And here you can see that the results from different data sets are practically indistinguishable. And basically we collected information on five lateral modes of vibration and 3 vertical modes. The fundamental mode of vibration in the lateral vibration had a frequency of 2.6 Hz, while the fundamental mode in the vertical direction has a frequency of 4.5, with about 4.5 Hz. Okay, but we have collected information about the overall geometry. We have collected from historical drawings information about the possible arrangement of the fill, but we need to complete some information with some other information about the thickness of the central arch and the lateral arch, but also on the thickness of the lateral spandrel, in order to use this information for building a finite element model. As I said before, 2 different finite element models were developed. One simplified that was used very quickly for a rough safety assessment of the bridge, and afterward a more complete model. Here you can see that we, after a sensitivity analysis using as target value the natural frequencies, we have decided to make an updating, an adjustment of the structural parameters of the bridge, of the uncertain structural parameter of the bridge, by distinguishing the bridge in 8 different materials. For each different material, or for each region, the Young's modulus was the uncertain parameters to be identified, and in the end we obtain a finite element, a refined optimal finite element model, for which we obtain practically the same mode shapes of the identified one, and also the difference between between natural frequency observed and numerical is very accurate, with the maximum difference being below than 1%. Coming quite quickly to the last bridge, as I said before, this bridge, the investigation of this bridge was basically supported and also promoted by Lombardia region. Between 2018 and 2020, a research program was performed between Lombardy region and Politecnico di Milano, and in this project 9 pilot bridges were permanently instrumented with different objectives and also different systems. In this case, tilt meters were used. The bridge, you can see here, an elevation of the bridge, we have 15 piles and 16 arches. The dimension of the arch of each arch is around 17.5 meters, and the bridge is crossing the Sesia River. Okay, we can see some picture of the bridge during at different point during our monitoring. Of course, we began to study this bridge, and we are also apparent some armoring intervention and deviation of the main river flow, and you can see that, for example, this picture dates back to 2002, this one to 2018, and then you see that the flow of the river was completely changed. So different armoring interventions were performed at subsequent times in an attempt to stabilize the sediments around the foundation. And the foundation, all the foundation were basically strengthened. The first rendering that we have found in the archives dates back to 1955, and the first 3 piles from piles number 9 to piles number 11 were strengthened, and you can see in this drawing. But in 1984, there was a more complete strengthening intervention interesting all the piles from the 4th until the 11th. So all the piles that are in the river. As I said, in this case, not a dynamic monitoring, but something more traditional, a tilt meter, a monitoring using 15 tilt meters that were installed in this position. Afterwards, we installed a weather station, an echo sounder, and an hydrometer, and 2 cameras in order to understand, for example, what was happening in real time on the bridge. During the first month of monitoring, our objective was mainly to understand the effect of environmental parameters on the rotation we measured. And the effect of the environmental parameters are quite clear. In fact, the measured rotation tends to clearly increase during summer, and the main driver of variation of rotation is the temperature, the outdoor temperature, whereas relative humidity and water level practically does not affect the measured rotation. But we have a lot of measurement of temperature because each tilt meter has a temperature sensor integrated in the sensor. In addition, we have a weather station, and in addition, there is also a public weather station at a distance of about 13 kilometers from the bridge. And so, for example, we try to establish which temperature sensor exhibit the best correlation with the measured quantities. And for example, if we look at this thermistor that is integrated in tilt meter T14, the second one that was the temperature measured by our weather station, so it's not the temperature. And in addition, the public weather station from ARPA, we can see that the determination coefficients are always very high, but the best ones are related to the internal thermistor at tilt meter T14, and so we adopted this thermistor for studying generally the correlation between rotations and temperature, and also for minimizing the effect of temperature. So let's look at the result collected in 2 years of monitoring, from January 2021 until December 2022. So here we can see the evolution in time of the measured temperature and also of the water level. But for us, it is very interesting to first look at the normal behavior. And the normal behavior of the rotation is represented by this tilt meter. In fact, you can see that there is no accumulation of rotation, and in addition, there is also a linear correlation between the temperature, the measured rotation, and the measured temperature. And for example, for this other tilt meter, T02 is in this position and T12 is in this position. Also for T02, the behavior is very close to the normal one, with a very small accumulation of rotation and an almost linear correlation with temperature. And of course, if we try to remove the temperature effect and look at the residual, what is done here, basically, we can observe that using 7 months for training and a simple linear correlation between rotation and temperature for removing or minimizing the temperature effect, you can see, for example, that the residuals are generally in control, so they generally belong to the range of plus or minus 3 times the standard deviation once we have removed the thermal effect. So we are talking about the residual. But in some position, something different happens. For example, in tilt meters T7 and T8 that are installed on the same piers, as you can see, we have both an increment of rotation in time, and we also lost the linearity of the correlation between rotation and temperature. And the same happens also for the other tilt meters installed on the same pier. Of course, if we try to work in terms of residual, so difference between the predicted rotation and the measured rotation, we obtain this kind of behavior, and you can see that at a certain point there is a clear deviation out of the acceptable range between plus or minus 3 times the standard deviation. But 2 comments are needed. First of all, the increase of rotation is very, very low, in the order of 0.04, 0.06 degrees centigrade. In addition, as you can see from this plot, but also from the previously shown plot, the 2 settlements are not simultaneous. A score-induced settlement should be simultaneous and involve the entire foundation pier arch system. So something happened for sure to the structure, very low as intensity, but not related to score. Coming in time to the conclusion, I was just to remark that operational modal testing and analysis was used to obtain important information on the presence of structural anomalies as well on retrofitting effect, and this was shown for the arch bridge over the Gesso River. But as we all know, operational model analysis is a key step for updating and validating numerical finite element model for structural assessment. In addition, the continuous monitoring of masonry arch bridges using tilt meters seems promising for early detection also of score effect, generally for the detection of the structural health, even if in the presented case study the observed anomaly was not associated to score. So, thank you very much for your attention, and if there are questions.